All right, so here we are for AP Physics linear motion. I'm not going to bother making solutions for all of these. I think the first ones were okay. Again, email me if you want to see any of these worked out, if you're really curious about them, and I will work them out and give you a video. Or if you just want to check your values or whatever, you can check with me and I'll let you know. I want to jump right to the last one, Speedy Sue problem, because there's a lot to say about that problem. So let's go ahead and try that. Speedy Sue, traveling at 30 meters per second, enters a one-lane tunnel. She then observes a slow-moving van 155 meters ahead, traveling at 5 meters per second. She applies her brakes, oh no, but can only accelerate at -2 meters per second squared because the road is wet. Will there be a collision? If so, determine how far into the tunnel and at what time the collision occurs. If not, find out what's the closest she gets to the van. All right. So we did a problem that was a little bit like this last year. It was a problem where you were running to catch a train that was taking off away from you. This one is considerably more complicated. Is it really? They're similar. They're similar in complexity. But anyway, let's go ahead and give this a try. So first, I'm going to draw my sketch, right? It's always a good way to start is with a sketch. So let's see. Right, there's my tunnel, right? And here at the entrance of the tunnel, right, we have Speedy Sue driving in her car, right? Driving too fast for conditions, right? Some might argue, hey, wait a minute, if we're inside the tunnel, is the pavement going to be wet inside the tunnel? Don't ask these questions. Don't ask these questions. Let's see. The wind in her hair, right? All right. And there we go. All right. Anyway, driving along. Now we know that she is going to be driving to start with at 30 meters per second, which is pretty fast. Okay. And up ahead, a distance of 155 meters ahead. meters. Say there is the back end of the van. All right. There we go. All right. And the van, we know, is traveling at a velocity of 5 meters per second. Probably too slow for conditions, to be honest, creating a hazard here. But anyway, 30 meters per second, it's only going 5. Clearly, she's going to catch up to and slam into that if she doesn't do something. So she slams on the brakes. And the brakes, though, only have an acceleration of -2 meters per second squared. So will she collide? If she collides, then how far in to the tunnel here does that collision? So we're trying to find this horizontal displacement to where they meet. Or if she doesn't collide, what's the closest they get? So what am I going to do? Well, it's an intersection type problem, isn't it? We're trying to see like when and if, these guys collide. So there's a couple different ways we could go about it, probably. I'm going to start by making the assumption that they do collide, right? Sure. And so what that means is I'm looking for an intersection. I'm looking for an intersection is when they have the same position at the same time, right? So I'm going to write an equation modeling position as a function of time for Sue, an equation for position as a function of time for the van, and then set the positions equal to each other, right? And then solve for the time when that occurs. That is the plan. So for Sue, okay, you say she's accelerating along. What kind of equation are we going to use? Well, we've got A, we've got V naught, and we're trying to find a position, right? And then time, right? When position is a function of time, we know when they're at the same position at the same time. So the variables I have are going to be, A and V naught and displacement and T. And so you say, well, gosh, the equation that's got those variables, that's this one. Delta x is V naught T plus 1/2 AT squared. Now, you know what I didn't do? that is a key part of solving an intersection problem is I should really drop a coordinate axis down on the world. So where would you like to call position 0? Well, you could call here 0, or you could call here 0, you could call anywhere you want 0. I think it's going to be convenient to say, let's make our axis here and call right here x equals 0, which makes this x equals 155 to start with, right? So delta x, that's final minus initial. So that'd be her final, the position of Sue minus her initial position, right? You say, but Sue's initial position was 0. Her velocity, her initial velocity is 30 meters per second. T, we don't know. I'm just going to leave that as t. Plus 1/2 her acceleration, -2 t squared. So this is an equation that has two unknowns, position of Sue and time, right? So I can plug in, if I knew the time, I could plug it in and find out where Sue was. Let's find the model for the van. Right? What do we know about the van? Well, it's going at a constant speed, right? And we know that that speed is 5 meters per second. And we want to find an equation. We know its starting position is 155. We want an equation for position as a function of time. It's going at constant speed, so the only formula that we can use for constant velocity is going to be the same one. But the fun part about this one is when you have a constant velocity, the acceleration is 0. So the acceleration drops right out. That whole term goes away. V naught and V are the same thing. If you've got constant speed, your starting speed, your ending speed, all your speeds are the same if you're going constant. So this is just going to be final minus initial, right? So it'll be position of the van minus the starting position of the van, which was 155. You know what I mean? So x minus x naught, equals 5 times t. So this is an equation that has position and time. Rearranging one last time here. The position of the van is given by the equation 5t plus 155. So I can put in any time and find out where the van was, right? Here I have an equation I can put in any time and find out where Sue is. In fact, let's tidy this up a little bit. Make it look pretty. Position of Sue is 30t minus t squared, right? Because half and -2. Okay, so here I have two equations, right, for position. What's my goal? To find out when they meet. And so they'll intersect when they're at the same position at the same time. So I'll set the positions equal to each other. So I'm going to write an expression. Position of Sue had better equal position of the van. Somehow I lost my color coding along the way. Did you notice that? So sad. The color coding is so helpful. All right, anyway, so if I do that then, position of Sue, that's 30t minus t squared. And I'm going to set that equal to the van's position, which is 5t plus 155. Look, I have an equation with just one unknown, t. I can solve this for the time when this holds true. Rearranging this mess, I always like to have my t squared term positive. So move that to the right side, subtract the 32. So minus 25t plus 155 equals 0. That's a nice quadratic there for us, right? I can make my calculator solve a quadratic equation, right? I'll go ahead and I'll use the solver function. That's the way I like to do it. Math, solver. See here, we got to put in my equation. We're going to say our equation is there's just a 1, let's see here, variable squared, right? Minus 25 times the variable plus 155. What's my starting guess for time? She starts off at 30. Starts at 155 meters ahead, 5 seconds, but she's been slowing down, so, and it's moving forward. We'll just say 7 seconds as our first guess, all right? See here, and let's go ahead and tell it to AlphaSolve. It thinks about it and says, hey, look, 11.38 seconds. That's a little longer than my first guess, 7 seconds, but okay. So it returns an answer of 11.38. Should I go down another digit? Nah, that's fine. But you say, wait a minute, Mr. C, I know that quadratics have 2 solutions. So let's try this again. I started at 7 and it got to 11. Let's go to the other side. I'm just going to put 20 in, all right? And tell it AlphaSolve. It thinks and it says 13.62 seconds. You say, okay, now why do I have 2 solutions? Well, it's like this, all right? Speedy Sue, slow van, right? Okay. Now the van's going on, tuk, 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 tuk. She's going faster, right? She's going to go, and then now you remember the equation just knows about things with this acceleration. It doesn't know about things hitting each other. So the equation says, I'm coming along and I'm going faster than the van, so I would collide, but I'm continuing to slow down. So eventually I would like pass back through, ghost back. So if I was like a ghost, I would go through the van and then back the van again, because I am getting, whoops, right? I pass it again because I'm getting slower and slower. So at first I'm going faster than the van, and as I hit it, and then I'd be going slower, and I pass back through it again. So you get two intersections there. The one that we want, of course, is the first one. Not that we want to collide, but that's the one that we first would contact. And so now the question that we're trying to find was not when do you hit the van. The question we're trying to find is how far into the tunnel and at what time the collision occurs. So we found the time. Now we need to know where we are. So I just have to put, they should both be at that same position at that time, right? So I could put this into either equation, either my model for the van's position or my model for Sue's position. I should get the same answer out. I'm going to put it into my model for the van's position because that looks like an easier equation to use. So if I took that and put it in there for t, what am I going to get? I'm going to get the position of the van is 5 times 11.38 plus 155. So how far into the tunnel does that collision occur? And I get a value of 211.9 meters into the tunnel as the position of the collision. Now you might say to yourself, 211 meters, that seems really long. That's like, a couple football fields. Yeah, this tunnel's that long. All right, hey, we're good with this, right? Now, a question that I sometimes ask is I say, all right, this is the answer, the official answer to problem 7, but what if Sue's brakes weren't so good, right? I mean, she lucked out here, right? No, she didn't luck out. I wasn't saying she slammed right into it. What if her brakes were better? Sorry. Whew. What if she'd been maintaining her car better, or if the road was not wet, right? And so her acceleration was greater, right? So let's try this problem again, all right? But let's say that her acceleration was a little bit better so that she's not going to collide with the van, right? Let's say that her acceleration, so same setup, but what if Sue's acceleration was negative 2.5 meters per second squared, right? So I'm going to follow through the same procedure, right? And I'll do the exact same thing. The only thing I'm changing is the acceleration. So when I do this, the position for Sue equation will look very similar. It'll be, again, I'm going to this line here. It'll be 30t plus 1/2 negative 2.5 t squared. And so the position equation for Sue will end up being 30t, what's a half of negative 2.5, minus 1.25 t squared. So that's Sue's equation. The van is going to stay the same. The position of the van will still be 5t plus 155. We're not changing anything about the van. And so now when I set the equations equal to each other, position of Sue equal to the position of the van. I do 30t minus 1.25 t squared equal to 5t plus 155. Okay, and I rearrange. I like to put the t squared term on the other side, so that's positive. So I have 1.25 t squared minus 25t plus 155, right? And if I do that and I solve my quadratic, right? With the solver program, I can just go up and grab that equation. But now, okay. So I'm going to say 1.25 variable squared minus 25 variable plus 155, right? Yep. Okay. And we're going to guess because we've got a pretty good idea where it was before, right? Before the collision was like 11 seconds, right? So we'll go ahead and we'll throw in like 11 as my starting guess, and we'll say alpha solve. And thanks. and it thinks, and it says, "Wah, wah," right? Error, no sign change. You say, what's going on? Why am I not getting an answer? And the answer is, we're not getting an answer because she doesn't collide. Those positions are never equal to each other. And you're like, okay, so there's no solution. So no collision. All she needed was just that little bit better acceleration, right? You're like, okay, great. But now the problem says, all right, if not, if they don't collide, determine the distance of closest approach between Sue's car and the van. I'm like, oh, how do I find out when they're the closest to each other, right? And so there's the approach we would have done last year in honors. And there's the super cool calculus approach. Which one would you like me to share with you? I know you already know the answer to that. I'm going to show both ways because that's the way I am. So I want you to see the super cool calc way, but we'll go ahead and do the do the physics, the first year physics way first. Okay, first year physics way requires you to have this insight and just recognize this fact. That fact is that as Sue cruises along, right? All right. As long as she's going faster than the van, she's going to be catching up. But once she slows down so that her speed matches the van, she's not catching up anymore. And once she goes slower than the van, now they're separating. So they're at their closest approach when her speed matches the speed of the van. Make sense? So when the van is going at 5 meters per second, she starts at 30. When she slows down to 5, that's the closest. She hasn't caught it yet. She's never gonna. She's just gonna slow down after that. So I just have to solve for where she is when she reaches a speed of 5 meters per second and where the van is when she reaches a speed of 5 meters per second, and then see how far apart they are. Make sense? So that's an approach we could use. That's what we would do last year. Gosh, do you need to see me run through that algebra? Nah, you can do that. You can do that. Yeah. You know I'm going to do it anyway, right? I almost talked myself out of it, but not quite. So what I want to do is I want to know when Sue reaches 5 meters per second, and knowing the variables a, v naught, v delta xt, right? Really what I want to eventually get is the position there. But I'm going to need that time for when I plug in for the van. So I am going to end up having to solve for both of these. But her acceleration is negative 2.5 meters per second squared. Her initial velocity is 30 meters per second. And the final velocity, we want to know when she reaches the same speed as the van, 5 meters per second. That's a special insight you have to have. Okay, want to find delta x first? T first doesn't matter. Let's go ahead and find delta x first. Actually, let's find t first. So I want the formula that doesn't have delta x. That would be this nice simple one. V is at plus v naught. And so that time would be v minus v naught over a. Plug in my values. So you're 5 minus 30 over negative 2.5. And you say, 5 minus 30, that's negative 25 over negative 2.5. Oh my gosh, that's 10 seconds on the nose. How nice. Okay. Can I solve for where she is at 10 seconds and solve for where the van is at 10 seconds? Sure, right? And so I say, okay, someone shows these numbers really well. Small pat on back. All right, here we go. Let's find how far she has gone. We'll go ahead and use delta x is v naught t plus 1/2 at squared. Why not? And so we'll find that Sue has gone initial velocity of 30 times 10 plus 1/2 negative 2.5 times 10 squared, right? So that's going to be what? 300, and then 100 times minus 1.25. That'll be, Yep. And so how far will she have gone? She'll have gone 175 meters into the tunnel is where Sue will be at. That's the final, because it's final minus initial, right? So it's x Sue minus the x initial, x of Sue initial, which is 0. Okay, so her final position is 175 when she reaches that same speed as the van. Where is the van? Well, let's see. The van, we had the equation that the position of the van is 5t plus 155. I'm just pulling this equation down from up there. And so we say The time we now know is 10 seconds, so it's just 5 times 10 plus 155. You say, hey, the van will be at 205 meters. This position of the van. So how far apart are they? Well, that's just the difference between these two. 205 minus 175, and you say they are 30 meters apart. That's the closest they get. Gosh, pays to take care of the road surface and your tires and keep everything safe. Alrighty, so that's the closest they get. But wait, I said there was a super cool calculus way, didn't I? Yes, I did. Yes, I did. So let me share the super cool calculus way. The super cool calculus way of solving this problem. Okay, so using calc, we have an equation for the position of Sue. We have an equation for the position of the van. We want to know the closest they get, right? You say, wait a minute, the closest. That's the smallest the separation distance gets. That's a minimum. Aha. You see the calculus coming in now, don't you? You say, hey, what is that separation distance? That's the difference between their positions. So that might be like the position of the van, right? Minus the position of Sue, right? That's how far apart they are. That's the separation. And so I could just make a function here, the position of van, which is 5t plus 155, minus the position of Sue, which is 30t minus 1.25 t squared, right? Right? And you say, hey, that's the function for position, right? For how far apart they are, the separation, right? I want to know when this is minimized. So I should just take the derivative, set it equal to 0, and find my minimum and maximum of the function, right? Okay, so can I take the derivative of this? Derivative of, this is really ugly. I should not have called that delta x. That was really ugly looking. But you know what I mean. I want to take the minimum. And so you say, hey, take the derivative of 5t. What's that? 5. Derivative of 155, 0. Now let's distribute that negative, okay? So negative 30t, I'm going to do this. I'm going to distribute the negative. Okay, is that cool? All right, so, okay, plus 0. And then taking the derivative of that would be minus 30, right? And then the derivative of this, that would kick a 2 out in front, right? It would be plus 2.5t, right? That is the equation. That's a plus 0 in case you're wondering. It's not 2, it's plus 0. Okay, so I've got 5 minus 30. That would be negative 25 plus 2.5t. Oh my gosh, that's the derivative. I'm supposed to set that equal to 0 so that I'm finding the minimum, right? You know what I mean? Here's my separation distance versus time. It's some kind of a graph here. They start off 155 apart, right? It's going to be a graph like there, right? Where this is the closest they get. It's the minimum there. And you say, look, well, what's going to make the 0? Oh my gosh, when t is 10. Look at that. Look how fast it is to take the derivative and, with the equations we already had. Calculus is super cool. Do I need to verify that it's a minimum and not a maximum? How would I do that? Well, wouldn't I just take the next derivative and see if it's positive or negative? What's the next derivative of this? 5, constant, 30, constant, 0, constant. What's the derivative of 2? It's just 2.5. So my derivative of that delta x function is just going to be 2.5. That's positive. Positive means it's shaped like a smiley face. It's a minimum. Woohoo! All right, so that's solving that problem, right, using calculus, right? Calculus is an awesome tool. You do all kinds of neat stuff with it. Everybody loves calculus, right? Hey, if I have not emphasized this to you yet, all right, I will make a point of saying this in class again sometime soon. When you're studying, the most important subjects that you take in school are your English class is your most important class. Why? Because being able to communicate is important to everything you do. Okay, your communication skills, your reading, your writing, you'll be able to understand and comprehend what you're reading and writing and hearing. Communication is super important. So that would be your number 1 class. Your number 2 class is your math class, because math applies so many places too. Okay, and mathematics is the language of the universe. You really want to get good at math. It is going to help you in your science. And so, as well as everything else you use math for. So take your time, make sure that you invest time in your math class, okay? Calculus, of course, is this incredible accomplishment in Western civilization. Developing calculus is amazing. And it is well worth it putting some extra time into studying your calc. If and I don't know how many teachers are going to tell you this, but if it came down, push came to shove, and you had to decide between studying your calc and studying your physics, in general, I'm going to say study your calc. I think it's more important than studying the physics. Yeah, don't tell the math teachers I said that. But anyway, but there you go. All right, calc, incredible tool. Hey, and that's the last problem on AP Physics linear motion. And I hope that it brought up some good memories from honors physics from looking at intersection problems and the main concept of how we solve for intersections.